In this video session, I would like to discuss about the work transfer. Now, in any thermodynamic systems, we have two energy transfers normally we consider. One is work transfer and another is heat transfer. In the work transfer, normally if you take a system is consisting of battery, and this battery is connected to some device, and this device is say rotating a fan. Battery is supplying current to a motor, and motor is performing some work of rotation of the fan. Now this is system boundary, and here we are getting work, and this is system, and this is surroundings. Now here the battery is performing, is trying to give some electric energy to the motor, and motor is doing the work. Now instead of this fan, initially it is a fan. Now we are getting work by fan. The net effect of this fan is, say, we can raise some mass. Like if you connect this motor to a pulley, the net effect of rotating the fan is raising a pulley W. Why you are using this? Because the work is measured in terms of the weight, force and displacement. Work is equal to force and the displacement in the direction of force. So here the net effect is raising the weight. So here in thermodynamic systems, instead of battery and motor, you are using some substance, and you are trying to heat a substance, and you are trying to get some pressure or some change in the system substance properties, and then you are going to get a effect of raising the work or lowering the work. Now we'll see that work as a displacement of the piston. So because we have to represent the work in terms of some equations, so consider a piston and a cylinder. Okay, and this is area, diameter, and this is L. So here the work is force into X. X is a displacement. Okay. Now this force can be given by pressure by area. Pressure divided by area, pressure multiplied by area. Sorry, pressure multiplied by area is a force, and A into X. X is a displacement. So P into dV. So work is nothing but P dV. Now for small dV you are trying to get. Now this is delta W. Now work is equal to integral dW, which is equal to integral P dV. Now here at this particular point of time, we can differentiate a path function and a point function. The work is said to be a path function because the work is taken from by the displacement of the piston. So if you draw a graph at this particular point 1, and the pressure and volume are changing simultaneously, and it is dropping to point 2. So the work is nothing but the area under this curve. Integral P dV. This is P to the power of n is equal to constant P dV. So this area is nothing but 1 to 2. So it is not an exact. It is not a differential. dW. If you say dW is equal to W2 minus W1, it is not possible. dW is not equal to W2 minus W1. It is a function of dW is P dV. But so W is not exactly differential. So but dV is a perfect differential. Integral 1 by P into dW. Because this 1 by p is an integral factor and dw is a inexact differential. So dv, this is equal to v2 minus u1. v2 minus u1 is equal to integral 1 by p into dw. So Vn here, P pressure, V volume, T temperatures. These are the point functions. P is a point function, V is a point function, T is point. At particular point 1, you have P1, V1 and T1. At point 2, P2, V2 and T2. And in between, P, V, T. At any point, it will be having a point values of P, V, T. But work is not, the work at point 2 we cannot see, and work at point 1 we cannot see. But we can say that the work between 2 and 1. So dw is not w equal to w2 minus w1, but it is equal to dw is equal to integral dw is equal to integral pdv 1 to 2. So this is a small discussion about a work transfer, path function and a point function. Thank you for watching the video.